This video is on catalysis. By the end of this video, you should understand what a catalyst does in terms of activation energy and collision theory. You should understand how various types of catalysts work, and you should be able to identify a catalyst in a reaction mechanism. A catalyst is a substance that speeds up a reaction rate without being consumed. In other words, it's not a reactant or a product. It's there at the start and it's there at the end, but it serves to speed up the reaction. It does this by lowering the activation energy. There are two main types of catalysts. A homogeneous catalyst is present in the same phase as the reacting molecule. Here you see that our reactant is H2O2, an aqueous solution, and our catalyst is NaBr, also an aqueous solution. This catalyst helps speed up the breakdown of H2O2. A heterogeneous catalyst is present in a different phase than the reacting molecules. It's usually in the form of a solid, as you see here. In this case, we have a solid metal surface acting as the catalyst. The catalyst is able to attract the reacting molecules, and when it attracts those molecules, it causes the bonds within the molecules to weaken, making it easier for those bonds to break to form new product. Let's look more closely at how a catalyst works. On this graph, the red line represents the energy profile for an uncatalyzed reaction. As we said, if we add a catalyst to the system, it will lower the activation energy. The green dotted line represents this lowered activation energy. Notice that the addition of the catalyst has not changed the energy of reaction, the difference between the energy of the reactants and the products. However, it has changed the activation energy and the energy of the activated complex. Let's consider this activation energy aspect in terms of collision theory. This green line here represents the number of molecules with any given energy in a system. As you can see, most of the molecules here have this amount of energy. Here, the red line represents the activation energy of the uncatalyzed reaction. Only molecules that collide with an energy above the activation energy will be able to be converted to product. However, if we lower the activation energy using a catalyst, more of our molecules will now have enough energy to overcome this activation energy barrier. Notice we haven't changed the energy of the particles, we've simply made the energy barrier lower. Looking at a more fine-grained explanation for how catalysts work, there's several different mechanisms that allow them to lower activation energy. Often they work by stabilizing a transition state, thereby lowering the activation energy. If the transition state is more stable, it's lower in energy. Occasionally, it can participate in the formation of a new intermediate, thereby giving a completely new pathway for the reaction to proceed, a pathway with a lower activation energy. The bottom line is, in either case, more molecules will be able to achieve the lower activation energy. Again, this does not change the energy or the enthalpy of the reaction, since the energy of the reactants and products remains the same. When considered within the context of biology, catalysts have a special name. A biological catalyst is called an enzyme. An enzyme is generally a large molecule with an active site that can interact with the reactants or substrates. These are often in the form of proteins, very large biomolecules. Again, by binding the substrate or the reactant to the active site, the activation energy of the reaction is lowered. Here's a schematic diagram. Since these molecules are so large, they're often just represented with these blobs here. Here you see the substrate or the reactant, which is another large molecule. And here's our enzyme, this blue shape here. Notice that the blue shape has a specific cutout that fits exactly to our substrate. This helps it selectively bind only the substrate it should be binding. This is often called the lock and key model, since only one key will fit in the lock. Once the enzyme and the substrate bind, they form a complex, which then allows for a lower activation energy for products to form. It's important to be able to identify a catalyst in a reaction mechanism. While a catalyst will not appear in an overall reaction, it may appear in a reaction mechanism. Recall that a catalyst is present at the beginning and at the end of a reaction in its unaltered form. Pause the video here and try to identify the intermediate and the catalyst in this reaction mechanism. When you come back, I'll reveal the answers. Welcome back. Since ClO was produced in step 1 and then used in step 2, it must be an intermediate. Chlorine, on the other hand, is present at the start of step 1 and at the end of step 2. Therefore, it's a catalyst in this mechanism. Again, neither the chlorine or the ClO would appear in the overall reaction. As you can see, both would cancel out when we add up these two steps. That brings us to the end of this video. Let's review our goals. First, we looked at what a catalyst does in terms of activation energy and the collision theory. Then we looked at how some various types of catalysts work. And finally, we learned to identify catalysts in a reaction mechanism.